Okay, hello everyone. Welcome to VSPG. Today we're hearing from Dr. Daniel Viete from Johns Hopkins University. So with a background in rock mechanics and engineering geology, Dr. Daniel Viete uses a mix of fieldwork, petrology, geochronology, and geochemistry to study the geological and petrological records of convergent tectonism. Particularly, he's interested in questions related to the timescale, rates, tempos, and drivers of conversion margin processes. He conducts work on the Appalachian Caledonian system, the Penokean and trans-Hudson orogenies, and on subduction zone complexes globally. Daniel received his PhD from the Australian National University, and afterwards he was a Fulbright visiting scholar at the University of California, Santa Barbara. And then he was the Marie Curie Junior Research Fellow at Durham University before joining the faculty at Johns Hopkins University in July of 2016. And he's currently still at Johns Hopkins as an assistant professor today. And today, Daniel will be talking about accretionary orogenesis and its features in the Phanerozoic versus the Paleoproterozoic. So we're really excited about this talk. Daniel, please go ahead.
Okay, thank you, Alex. Can you hear me okay?
Yep, we got you.
All right, great. Thank you, and thank you everyone for showing up. I'm excited to talk about this today. I'm going to talk about accretionary orogenesis, and I'm going to focus on an example from the Paleozoic and compare that to an example from the Paleoproterozoic. So my name's Daniel Viete. I'm from at Johns Hopkins University. It's only my name on this slide, but there are a host of different collaborators, current and former PhD students, and postdocs who were heavily involved in this work. This work is mostly done at Johns Hopkins University, and I will shout out those people along the way. So let's get started. All right. So what is accretionary orogenesis? This is a figure from the 2009 paper from Kaywood et al., which was a review of accretionary orogenesis through time. You can see here that Kaywood et al. Pointed out on the east side of the Pacific here, we have Cordilleran accretionary orogenesis, and then they called the Alpine Himalayan orogen a collisional orogen. So for the purpose of this talk, I'm going to define accretionary orogenesis as orogenesis that involves subduction in some sense. But there are a couple of things that I just want to point out here. So first of all, the geological record requires the involvement of continental crust. So in further back in geological time, of course, accretionary orogens have some continental crust in the overriding plate. And as well as that, I want to point out that accretionary orogenesis, as I define it, can involve continental collision, but it involves microcontinent and rim continental collisions, as well as the collision of juvenile terranes, arcterranes, the rest of it. Okay, so why is it important? This figure here shows the global distribution of convergent margins, and colored in black here are subduction margins, and in gray collisional margins as defined by Walter in 2010. So about 75% of the Earth's convergent margins are subduction zone margins where convergence is accommodated by subduction zones. So on Earth today, accretionary orogenesis is the dominant mode of orogenesis. And as well as that, I just want to point out that throughout the alpine system, there are subduction zones and there are these residual pieces of oceanic lithosphere. And so, the alpine part of the alpine Himalayan system is still in accretionary mode in some senses. The Himalaya are the type example of continental collision, true continental collision, and of course it comprises a tiny amount of the total amount of convergence on Earth today. So why else is it important? It's also important in terms of the geological record. So some of the key geological features that we talk about and that we teach in introductory geology are associated with these accretionary environments. So here I've got a few examples. On the left here is ophiolite belt described by Bird et al. In 1971 along the Appalachian origin. I'm going to go into a little bit more detail here in this talk on this belt. On the right here, I've got some images of different sedimentary environments, different basins, and you can see that the top two here are accretionary environments, and you can see the huge diversity of different depositional settings and basins that are available within these accretionary environments. So a good deal of what we know of the sedimentary record is associated with these accretionary convergent settings. On the left here, we have paired metamorphism, this classical concept proposed by Miyashiro in 1961, whereby we have a relatively cold metamorphic belt representing tectonic downwelling, and inboard a relatively warm metamorphic belt representing tectonic upwelling. So this is another key classical geological feature that's associated with accretionary orogens. And something that the talk will focus on a little bit today is also Barrovian regional metamorphism, or Barrovian style regional metamorphism. And this is metamorphism of the middle crust, which occurs in association with orogenesis. So it's an orogenic feature, and I'm going to propose that for the most part, this is dominantly an accretionary orogenic feature, although it's often associated with collision. All right, so on this topic of Barrovian regional metamorphism, I have to give a little bit of a primer prior to diving into some of the data that and observations I'm going to present. So orogenic regional metamorphism occurs within the middle crust during orogenesis, and the heat sources are not very well understood, and there is still debate surrounding them. I've put up here two end-member models for the heat associated with orogenic regional metamorphism, Barrovian-type regional metamorphism. So on the left, we have heat advection from depth. And so this was the original proposal of Barrow to explain the metamorphism that he mapped and described in 1893. And so in this case, there can be different mechanisms, but mafic magmatism can transport heat from the mantle where those mafic magmas are produced into the middle crust and provide some heat for orogenic regional metamorphism. Barrow himself stated that he did not see a difference between contact metamorphism and regional metamorphism in his sequence. And so this would be effectively transport of heat into the middle crust via magmatism. As well as that, any process that attenuates the thickness of the lower lithosphere brings the asthenosphere closer to the middle crust where the metamorphism occurs. And this decrease in the heat source can then cause a much more transient thermal feature. So tectonic attenuation could involve some detachment with preferential thinning of the lower lithosphere as opposed to the upper lithosphere, or it could involve catastrophic loss of the lower lithosphere, potentially also slab breakoff. The other end-member model is that of thermal relaxation, and this was born of numerical models that were produced during the 70s and 80s, which directly linked regional metamorphism to crustal thickening. And so within these models, there was a phase of rapid crustal thickening, which basically took rocks to depth, relatively cold rocks to depth, and burial. And this was followed by internal heat accumulation by radiogenic decay, plus some conduction from the base of the lithosphere, so a more distal asthenosphere. So once the system is hot, then advection via erosion and exhumation could then bring the heat from depth back towards the surface. Now, there are a couple of features of these two models which allow them to be distinguished in terms of what may be operative. So in the case of the heat advection from depth model, the thermal event is the perturbation. It is the tectonic perturbation. So when the tectonic effect occurs, that's when heating occurs. And it's associated with rapid prograde heating relative to the thermal relaxation model. And it should be relatively limited in length and time scale because the system is attenuated and the heat sources are brought closer to the region. In opposition, the thermal relaxation model records a return to thermal equilibrium following the initial tectonic perturbation. And as well as that, prograde heating should be relatively slow, and the scale of the metamorphic sequence should be much larger in association with this time length scale relationship here. So when it comes to accretionary orogenesis, just want to point out, two conceptual models which could accommodate either of these two heating scenarios. So looking at the Andean system here, which has been overthickened for a long period of time and relatively stable, could have a situation where over many tens of millions of years, a heat source is, thermal relaxation is allowed to develop within the middle crust, leading to Barrovian-type metamorphism. On the west side of the Pacific here, where we have all these continental ribbons and juvenile terrains and this mishmash of different subduction zones, we might envision a different style of accretionary orogenesis. And so this figure here shows a style whereby subduction initiates, is terminated, there is abduction, there is a polarity flip, and this is a much more hyperactive model. There is hinge retreat and advance, which can lead to thinning and thickening of the overriding continental plate. And there are situations here where you may get this thinning of the lower lithosphere, potentially decompression, melting of the asthenosphere, and these episodes of mantle heat input. And so you can see that there are two styles of accretionary orogenesis that could accommodate these two different end member heating scenarios. So in this talk, I'm going to focus on a couple of things. So I'm going to focus on ophiolite belts, and I'm going to focus on these orogenic regional metamorphic complexes. And I'm going to focus on the Appalachian Caledonian system as a model for Phanerozoic plate tectonics and accretionary tectonics. And then I'm going to compare that to an older example from the Paleoproterozoic of the Lake Superior area. So first I'm going to bring constraints from the Paleozoic Appalachian Caledonian system. This will include constraints from suprasubduction zone ophiolites on the start of tectonic convergence within this system along strike. And then also some timing, some suggestions for the timing of the terminal continental collision to form Pangea. Well, first Laurussia and then Pangea from the literature. So once I've gone through that, then I'm going to present a little bit on the context for regional metamorphism, focusing on the classic Barrovian sequence from Scotland and the associated Ireland, the associated regional metamorphism in Ireland. So I'm going to look at the timing relative to this subduction initiation event and final continental collision. I'm going to try to constrain prograde heating rate, magmatic and structural associations, and as well look at this idea of whether there may have been multiple regional metamorphic episodes. And so we'll take all of this and compare it to what we find in the Paleoproterozoic Lake Superior area. So use some direct testing for these above features from the Phanerozoic record, applied within a uniformitarian framework, whereby we assume that the observations and the models that are relevant for today are also relevant for the Paleoproterozoic. We're going to look for what looks similar or comparable, and what may seem different. So let's go. So in terms of the ophiolite belt part of the talk, I'm looking at the record of iapetan subduction initiation, and I've taken my directive from these geologists that were working during the early times of plate tectonics. So John Dewey, Bird and Kidd, and there's a call here to go and study the ophiolite belt. So details of the history of the Proto-Atlantic, this is now called the Iapetus Ocean, can be elucidated from a study of the ophiolite suites in the Appalachian Caledonian system. So about 40 years later, there was another finding or suggestion, which has driven the work I'm about to present. And this was from Bob Stern and others who had been working in the Isubon and Marianas forearc of the West Pacific. And they said that if you want to understand subduction initiation, you study forearc crust, which develops during subduction initiation. And to understand forearc crust, you study ophiolites. So what they meant by this is, here is a schematic which shows how subduction initiation is thought to progress. There is the initiation of subduction, and the first event at T1 is some seafloor spreading in the forearc region, creating this forearc oceanic tract. And as the system evolves, you get to some arc magmatism and these nascent island arc systems, and eventually a mature island arc system is overprinted. And so within the Isobonon-Marianas system, these data from Reagan et al. In 2010 of lavas from the Isobonon-Marianas system show that the lower stratigraphic levels of volcanic stratigraphy have morb-like geochemistries, which are consistent with a source in decompression melting, and so consistent with an origin in this forearc spreading. But at higher stratigraphic levels, start to get what are called bonanitic lavas after Bonin. And so these are representative of this transition towards arc magmatism from the early forearc spreading. And so there is these green units, these morb-like units, these forearc basalts that appear low in the stratigraphy. And as one works through the volcanic stratigraphy, you start to get these more depleted arc-associated, very nascent arc-associated magmas. And so this here is a signature of subduction initiation, or has been proposed to be a signature of subduction initiation. And as well as that, if we can date these earliest magmas, then we can put a date on this process of subduction initiation. And so taking these lessons, well, the call from Bird et al., and then these lessons from Bob Stern and others, we went to the Appalachian Caledonian ophiolite belt and tried to put some, first test for a subduction initiation association, and then put some timestamps on this. And so this is work that was led by my former PhD student, now at the USGS, Dr. Naomi Becker. And so for the Lekker ophiolite of central Norway, we can see we have this subduction initiation signature. If we move down the system, in Baltimore, I'm currently sitting on the Baltimore ophiolite, and it has the subduction initiation signature. And as well as that, down the end of the Appalachian system in Alabama, the Dadeville complex has this same subduction initiation signature, whereby lavas become more depleted up section, and they move from a forearc basalt chemistry to a more bonanitic chemistry. These black lines are the average bonanite chemistry from that 2010 Reagan paper. All right, so there are a whole bunch of these supersubduction zone ophiolites with these signatures along the Appalachian Caledonian system, and we have gone off and used chemical abrasion ID TIMS dating to put really precise constraints on the earliest lavas and associated magmatic units. And so you can see from Lekker in the north at 491 million years ago, there is an age progression in subduction initiation such that it occurs progressively later, down to about 24 million years later, 6,000 kilometers down the system. Now, all of this dating was done in association with Jim Crowley at Boise State in their labs there. So these data here can be placed in a framework of distance and time. So I'm going to use this little plot a little bit. Each of these stars represent one of those dates on the last slide. And so you can see that on the x-axis here is years before present within the Appalachian system. And this is a long strike distance. So from Svalbard in the north to Alabama in the south, we've got about 7,500 kilometers in total, and 6,000 kilometers that are covered by our ophiolite subduction initiation constraints. And so you can see that subduction initiation gets progressively later, and it's about linear, about constant rate in terms of the propagation southward through the Iapetus Ocean. So as well as that, we can place some constraints on the timing of continental collision in association with the Appalachian Caledonian system. So in Baltica, it's thought to be relatively early. This is in the Scandinavian sector. So this is collision between Baltica and Laurentia. But in the Appalachian and Scottish and Irish Caledonian section, the collision between Gondwana and La Roche is at about 300 million years ago. So we've got all of this time in here between subduction initiation and collision, during which accretionary orogenesis is happening. And so if we go back to the Barrovian metamorphism of Scotland, this is Barrow's map from 1912 showing the different isograds here that define this progressive regional metamorphism. It must have occurred sometime between, if it's associated with accretionary orogenesis, sometime between the initiation of convergence with subduction initiation, the earliest ophiolites, and the collision. And so work published as part of my PhD work in 2013 has provided some constraints on the Barrovian metamorphism and its associated orogenic episode. So I'm just going to go through and look at the timeline as constrained by geochronology. So first of all, we have some dates here, which are uranium-lead zircon dates on migmatites. These date high-grade metamorphism, and they range 475 to 470. These are supported by samarium neodymium garnet dates from Ethan Baxter, back when he was working in this area as well. And so we got peak metamorphism at about 475 to 470 million years ago. There are some argon-argon white mica dates on metasediments, which start at about 461 million years ago, which means that the system had cooled through about 400 Celsius by then. There are a suite of bimodal intrusive units called which are dominated by gabbros, which I call here the Grampian gabbros, but Reed called the newer gabbros. So these are the same age as peak metamorphism. So they range in age from about 475 to 470 million years ago. These are uranium-lead zircon dates on the gabbroic units themselves. And this suggests that mafic magmatism was syn-metamorphic, and that there was some provision of mantle heat carried by these mantle melts into the middle crust during the Barrovian metamorphic episode. Work published in 2017 provided a samarium neodymium garnet date from the Ballantrae ophiolite as the earliest indication of collision in the system at 478 million years ago. And our recent work has put a uranium-lead zircon date on the Butte ophiolite, which is an associated ophiolite, at 487. So we have here some constraints whereby convergence began at about 487 million years ago. The first evidence of collision of the juvenile terrain with the margin is at about 478. There was peak metamorphism within several million years of that, and then cooling was relatively quick as well. And so we can put this into a temperature time plot. We have some ophiolite abduction event. The temperature is not very well constrained here, but I'm assuming at about 300 degrees Celsius, the rocks may have been buried and somewhat warm. But certainly the argon, the argon patterns are still detrital in the low-grade zones. And so there was some heating to peak metamorphism by about 475, and then subsequent cooling down to white mica closure. And so this requires prograde heating rates of on the order of 40 to even 150 degrees Celsius per million years, depending when during this box peak metamorphism occurred and what temperatures and time the initiation of accretionary orogenesis had. So using this, we can put a little box here on this plot showing the timing of the Barrovian regional metamorphism and the associated Grampian orogenic episode. This is the time from the 478 million year age to the 461 million year cooling age. And so we have an orogenic episode here, which is associated with Barrovian regional metamorphism. And we can go through the system and through the literature. I don't have all the references listed here, but these are different examples of regional metamorphic episodes from across the Appalachian Caledonian system. And you can see that they scatter but they can be sort of grouped into different events. And these events are being given formal names. So the Grampian tectonic is the early event that closely followed the initiation of convergence. And then there is a later Akkadian, Neo-Akkadian event, which I've taken the liberty of stretching further south into the southern Appalachians, but is defined in the north. So what do we have here? We have some features that we've constrained of the Paleozoic Appalachian Caledonian system. So first of all, we have an Iapetan supersubduction zone ophiolite belt, which becomes progressively younger south, covers about 6,000 kilometers of the Iapetus Ocean and about 24 million years. And these are the earliest evidence that we have of convergence in the Appalachian Caledonian system. So they're used to signify the onset of convergence. Regional metamorphism, in many cases, including the classic Barrovian metamorphism, closely followed this subduction initiation. And were associated, therefore, must have been associated with rapid prograde heating. So these rocks got to peak temperature over relatively small time frames, small intervals, following the initiation of accretion. In the case of the Barrovian, we see gabbros associated with the Barrovian, and this suggests that some form of decompression of the mantle and potentially some mantle heat contribution towards that metamorphic event, which occurred over short timescales and involved large rates of prograde heating. As well as that, in the regional metamorphic timing, we see distinct regional metamorphic events associated with distinct orogenic pulses. And so this suggests some episodicity in terms of the history of the accretionary history. And these can either emerge from internal organization or cyclicity within the overriding plate, or they could reflect changing geodynamics of the subduction accretion system. So potentially the arrival of some microcontinents or juvenile terrains, and then some outboard changes to the dynamics of the subduction and the boundary forces in play. All right, so I've kind of got a little bit of a description, a little bit of some constraints on the Appalachian Caledonian system, and now I want to move to the Precambrian and make some comparisons with Paleoproterozoic North America. And so this figure here is from Paul Hoffman's 1988 paper, United Plates of America. And this was, I'm not pretending that I'm the first person who's ever made, taken this uniformitarian approach to comparing modern systems as they're understood by geology to Paleoproterozoic systems. Paul did this fantastically well in this paper. But today I'm using this map just to show the area that I'm going to focus this approach on. So this is the Penokean area of the Lake Superior, the Penokean orogeny within the Lake Superior area of Wisconsin and the Upper Peninsula of Michigan. So the Paleoproterozoic of the Lake Superior area, this is the broad geology. This is a map from a paper that we have in preparation at the moment. So this is a map of the Paleoproterozoic origins with orogenic records within the Lake Superior area. We have an external domain. These are some margin sediments in this red-brown. And then there are some juvenile terrains, which are termed the internal domain in this region south of the Niagara Fault Zone. These juvenile terrains carry evidence that may be associated, that may suggest that they are orogenic ophiolites. So I'm going to cover that a little bit. In particular, in this region just south of Niagara Fault Zone within the Pembine-Wassail terrain. So a couple of questions that my group has sought to address are, does the mafic volcanic stratigraphy in these juvenile terrains preserve the supersubduction zone geochemical signature that Bob Stern and others have put forward for subduction initiation? And so are these ophiolitic records potentially of subduction initiation, the onset of convergence during the Paleoproterozoic? As well as that, these white dashed little nodes are some examples of orogenic of isograd sequences, which were mapped by James in 1955. And so we have in this region of the Upper Peninsula of Michigan, we have multiple examples of chlorite, biotite, garnet, sterolite, sillimanite, isograd sequences. And so we can test these to see if we see the same rapid prograde heating rates that we do in the Barrovian, and any association with mafic intrusions. As well as that, we can look for any evidence of polymetamorphism, as we saw with the multiple orogenic episodes and associated regional metamorphisms from the Appalachian Caledonian system. So let's go. So the Pembine ophiolite, shout out here to George Geis and Robert Holder, who are both postdocs here at Johns Hopkins University, and both heavily involved in this work, with George leading the work. So this figure here is from a paper in 2023 with George's first author. The study area is here, right at the edge of the Pembine-Wassail terrain, and you can see a close-up of it here. This is one of the only areas of, it's in Wisconsin, of the Lake Superior area that has really well-exposed outcrop of the Pembine-Wassail terrain, these juvenile terrains. So we sampled extensively within the area of good outcrop, and looked to try and characterize geochemical variation from the lower stratigraphic levels close to the Niagara Fault. This is thought to be the abduction thrust, to higher structural levels more distal around the town of Pembine, after which this package is named. And so what we found was that in the lower parts of the volcanic stratigraphy, there are morb-like mafic rocks. And as you move up to higher parts, there are bononite-like mafic rocks. And so this is consistent with this signature of subduction initiation that's being put forward from the IBM. So taking this uniformitarian approach, we found what we might expect if this is a supersubduction zone ophiolite. And George took it a step further and made comparisons with the supersubduction zone ophiolites of the Tethyan system. So those from Europe across to West Asia, including in Cyprus and Oman. And you can see that the stratigraphy is similar in the sense that that there is a morb to bononitic progression. There is a whole bunch of plagiogranites that intrude, which must be younger. We're missing a sheeted dike complex in the Pembine, but otherwise we have very similar features. I'll point out, and this is something that I'll revisit, the volcanic stratigraphy seems to be much thicker than it is in the Phanerozoic examples. We weren't able to get any zircons from the volcanic stratigraphy itself, but we did find some constraints from some of the intrusive bodies. This is a diorite body here, which is dated to about 1870 million years ago. And interestingly, there was a gabbroic body, which it was much younger, about 100 million years younger, 1770. And so this is about the timing of the Yavapai episode, which also affects the region. I should actually go back and point these out. So within this region, there are different Proterozoic accretionary orogenic episodes that are recognized. There is a first of all, there's a Penokean episode which is preserved in this area, which is about 1870 to 1820 million years ago, and subsequent to that is a Yavapai episode and then a Mazatzal episode. It's supposed to be 1700 to 1600. Okay, so as well as these two units, there are other published data from the Pembine area, and this here is the 12-foot falls diorite. It's a dioritic body that that intrudes the volcanic stratigraphy of the Pembine area, and it has a pretty precise date of 1888 million years ago. And so what we have is supersubduction zone, a volcanic stratigraphy that appears to have this supersubduction zone signature, which has been associated with subduction initiation. There is a constraint from an intrusion which requires it to be older than 1888 million years ago, and it's associated with the Penokean orogeny. And this map here is from Siborovsky et al., and it shows the large-scale, large igneous belt of large igneous provinces in red here. And I've used it just to point out the location of some other ophiolites along this same Paleoproterozoic accretionary system. So we have the Pembine ophiolite here. This number 2 here is a Flin Flon Snow Lake ophiolite. This was proposed by Stern et al. In 1995 on the basis of bonanites there. And the constraint on that is similar to the constraint of the Pembine ophiolite, so greater than 1889 million years ago. As well as that, we have the Pertonique ophiolite, which is up here in association with the Cape Smith belt, and the constraints are not so good for that. There was a recent paper from 2025 that suggests that it's older than 1815 and younger than the Archean. So it's possible that these are very similar in age and may comprise a similar ophiolite belt to what we see in the Appalachian Caledonian system. And so this obviously requires more work, but there may be a 3,000 kilometer belt here that is very similar to the Appalachian Caledonian belt that we've described. All right, so isograd sequences in the Lake Superior area. So moving on to the Barrovian-type metamorphism. So I need to shout out Shaprotik Roy here. He's a PhD student currently at Johns Hopkins University and is leading the work that I'm about to present. So this here is the map of James in 1955, and you can see the various isograds that were mapped, and they define different metamorphic nodes. So in the north here is the Republic node. In the west is the Watersmeet node. And down here in the Wisconsin-Michigan, near the Wisconsin-Michigan border is the PV node. And so I'm going to focus on the PV node a little bit. Now, I just want to point out that the isograd set in the PV node is similar in spacing and overall scale to the classic Barrovian sequence. So these two maps are put in at the same scale, and you can see that the length scales of metamorphism are comparable. All right, so the PV node isograd sequence, so it's located down here in association with these more compressed isograds, and this is the regional map here. The Selimonite isograd fell off, but it runs like this. And so this is the PV node area, and the isograds in the area are recorded within a metasedimentary formation within a sedimentary formation called the Michigane Formation, and these interpreted to represent foreland turbidites. Importantly, the Sudbury ejection, and they're within the Baraga group. Importantly, the Sudbury ejecta layer, dated to about 1850 million years ago, occurs at the base of the Baraga group and below the Michigane Formation, which means that these things were deposited after 1851. And this is work from Bill Cannon, published in 2010. All right. In the PV pond area, in the PV node, these isograds here, the orogenic regional metamorphic sequence, surround this brown unit. And this brown unit is a Gabroic complex called the PV pond complex. So just as for Scotland, this is a map of Scotland from Patterson and Goldsmith, the blue units are the newer gabbros, the Grampian gabbros, and you can see that the isograds, which are the different colors here, the Selimonite isograd, high-grade isograd, follows and occurs in a spatial association with these Gabroic bodies. It's the same deal at in the PV pond. So regional metamorphism is associated with a potential source of mantle heat and also a potential indication that the mantle had undergone decompression. The timing of metamorphism can be constrained in structural terms. So there is a strong deformation recorded within the PV node area, and you can see that it wraps the porphyroblasts associated with the regional metamorphism, and there is an internal fabric, an earlier internal fabric, which in cases is straight and high angled to the outside fabric, and in other cases is crenulated. And so these observations constrain the timing of regional metamorphism to syn deformation, major deformational, so syn D2. As well as that, the PV pond complex structural mapping within the area has shown that it contains a fabric with similar orientation to the dominant fabric in the metamorphic package. So you can see these stereo nets here show a consistent orientation or trend strike of the regional fabric. In the case of the metasediments, this is an S2 fabric with the earlier fabric preserved within microlithons. So there's an S2 fabric with the earlier fabric preserved between in the microlithon domains. In the case of the PV pond complex, a fabric of the exact same orientation is preserved, but in those meta-igneous rocks, it is the first generation there. So this constrains the PV pond complex mafic magmatism to also syn D2 and therefore syn regional metamorphic. As well as that, rafts within the PV pond complex, you can see here, we got a boat out to these things, and the fabric within these rafts matches the fabric in the outer parts, which suggests that the entire complex was assembled and overprinted by syn D2 metamorphism. By the D2 metamorphism. In terms of the timing of the PV pond complex, Shaprotic was able to locate some zircons from some of the gabbros. Here are some laser data from our lab downstairs here at Johns Hopkins. But Shaprotic went on to MIT to work with Jahan Ramasani and Dr. Lyle Nelson here on trying to get some more precise dates on the PV pond complex. And the dates come out to between 1835 and 1828 million years ago. So the PV pond complex and the gabbroic magmatism occurred at about 1830 million years ago, as did the regional metamorphism, which is constrained by a relative timing to be the same. In terms of a constraint on the earlier side, the Michigame Formation deposits have a kind of weird detrital zircon pattern. They have a strong population associated with the local Neo-Archean rocks, which form the basement, and associated with the Superior province at 2600. But as well as that, there is a really strongly represented second population, which is syn-orogenic. It's Penokean in age. So here it's about 1800, but some precise dating done at MIT has constrained these detrital zircons to 1846 plus minus 1 million years. And so this gives a maximum deposition age of 1847, meaning that the rocks that were taken to selimanite grade conditions, approaching 700, 650 degrees Celsius, were deposited, and that 650 degrees Celsius at 1830 million years ago were deposited after 1847. And so from this, we can go back to, this is the temperature time history of the Barrovian metamorphism, and we can overlay the Penokean metamorphism. And again, the PV node metamorphism. And again, we have evidence that prograde heating was rapid. So on the order of 40 degrees Celsius per million years or more. Of course, this constraint here is a maximum deposition age. So this line could be brought up and this would require much more rapid prograde heating. One final observation from the Lake Superior area, we have Shaprotic extracted some monazite and was able to date them using laser ablation ICP-MS. He's moving on to try and use more precise dating approaches to get some better constraints on these. But these are consistent with the 1830 million-year-old metamorphism. So with the PV node being representing peak metamorphism at about 1830. Interestingly, the ages are the same over several hundred kilometers along this southernmost part of the margin. For the Republic node, a storolite grade sample that Chiprotic dated by uranium-lead monazite gave a significantly younger age. And so this 1770 Ma age is Yavapai in age and is the same as the Gabbros, these Gabbroic units that we found in Pembine, these intrusives. And so again, we have just like the Appalachian Caledonian system, we have metamorphic episodicity, whereby we have multiple events recorded within the region. So the comparison reveals some similarities. So from the Scottish Caledonides and the broader Appalachian Caledonian system, we see that there is a supersubduction zone ophiolite belt, which presumably, which we interpret to record southward propagation of subduction initiation and earliest Iapetan convergence over 6,000 kilometers of the Iapetus Ocean between about 491 467 million years ago. Regional metamorphism in many places, particularly in Scotland, rapidly follows this subduction initiation. And so this requires prograde heating rates that are significant, greater than 40 degrees Celsius per million years. And there is a Gabbro association in Scotland and Ireland, which suggests that there is some decompression melting of the asthenosphere and some transfer of heat from deeper parts of the system into the middle crust, contributing in some way to the orogenic regional metamorphism. As well as that, we have evidence of distinct orogenic pulses and associated regional metamorphic events. And so this episodicity presumably results from some events associated with the geodynamics of subduction and accretion. In the Lake Superior area, we have one orogenic ophiolite, but there is potential that there are other ophiolites of very similar age along 3,000 kilometers of the Circum-Superior belt. And so this would be sort of an equivalent observation to what we see in the Appalachian Caledonian system. Regional metamorphism occurred within something like 8 to 12 million years of deposition of the metasediments that they affected, and all the way up to selimonite grade. And so again, this requires really rapid prograde heating. And again, in the case of the PV node, we see an association with large-scale gabbros that, spatial association, but also a temporal association. And this suggests that there was contribution of heat from the mantle towards regional metamorphism during the Penokean orogeny. And as well, the monazite data show that the different nodes are different ages, and this suggests distinct orogenic pulses and regional metamorphic events. So again, we have evidence of episodicity associated with different orogenic events. And so I'm not going to pretend that I'm the first person who has kind of observed this sort of episodicity. These are two models for the Penokean orogeny, one from Schultz and Cannon in 2007, and a much more recent one from Xie et al. In 2022. And so you can see that there are, a lot of changes happening in association with different subduction zones coming and going, abduction, the arrival of microcontinental terrains, and this drives this sort of episodic history. And it looks a lot like the Appalachian models that have been proposed. In this case, we have a different type of model where subduction polarity never changes, but there is this retreat and then advance of the subduction hinge, leading to pulsing, orogenic pulsing in the overriding wedge. And this looks a lot like the model that I introduced earlier. So I just want to finish. This is the last slide. I just want to finish with just by pointing out that there are some important differences. I pointed out earlier that this volcanic stratigraphy at Pembine appears to be much greater than the stratigraphy associated with Phanerozoic, the volcanic stratigraphy associated with Phanerozoic ophiolites. In the Michigame Formation metasediments, there is a really strong signal of syn-depositional zircon formation and delivery. And so it may not be that we're able to provide such, as well as that, we have the Sudbury impact layer, which constrains deposition as well. These constraints on deposition to peak metamorphism may not be as available in younger systems. This paper from Siborovsky, the red units here illustrate a circum-superior belt of large igneous provinces of mafic, ultramafic complexes, which are not a feature that we really see in Phanerozoic systems. And of course, there are the economically valuable banded iron formations within the Lake Superior area, which are associated with the lead up and the early stages of the Penokean orogeny. And so, yeah, I shouted out some of these people, but my acknowledgement, there are many people involved in this work and several funding sources. So I'll finish there and take any questions. Thank you.
Thanks, Daniel. Great. We'll go ahead and transition to questions and discussion. You can ask a couple ways. You can raise your hand. That raise hand button is go to the bottom of your screen, click reactions, and the raise hand button is right there. You can also go ahead and type it into the chat, and I can read it aloud for you.
Do you want me to stop sharing, or should I leave this up?
No, you can leave it up because some people might want to reference one of your slides. Let's see. Nicholas Swanson Heisel, please go ahead.
Hey, thanks for the great talk, Daniel. Fascinating to see how this work is progressing. I guess my question is just your thoughts on the origin of the Republic node in terms of what's driving that particularly sort of high grade and sort of bullseye pattern, right? You highlighted the similarity to the Barrovian of the PV node, but it's sort of like stepping inboard substantially later is still, I don't have a sort of clear mental model, and I'm curious what yours is.
Yeah, so I mean, I'll go back to the Isograd pattern. Yeah, here. So I'll remove the stars. Yeah, there are a couple of sort of primary observations here. It's much larger scale, and of course the dip of the Isograds will have some influence over that. With the PV node, it makes sense that it's a bullseye pattern. There is a heat source right in the middle of it. There is no such heat source within the Republic node. Yeah, so it's larger scale, it's later, it's further into the hinterland, and we're not so there's no obvious heat source there. It might be associated with some sort of juxtaposition of hot and cold terrains later in the orogenic history. So we're not sure, but we are working on it. So one thing that Shaprotic, the PhD student I mentioned earlier, is doing is a transect, a white mica transect from the chlorite zone into the staurolite zone. And we're looking to see the position where the white mica patterns move. We've already confirmed that in the lowest grades, the white mica patterns are detrital in origin, and then they're reset as you move upgrade. The exact position of that resetting and the size of the white mica grains can be used to do some forward diffusion modeling to try and constrain the duration of heating in the biotite zone. So we're hoping to at least get some constraints on metamorphic duration, which might help us to understand sort of scale through these length time scale relationships with conductive heating, conductive thermal transfer. But yeah, I don't know precisely. We're working to try and deliver some more information that we could use to try and assess how this works. But this would be the equivalent of the Acadian in the Appalachians, with the PV being the equivalent of the tectonic. Sorry, I couldn't give any more.
No, great. No, that was super useful. Fascinating.
There was just a comment in the chat from Marcia. I believe the Republic and Waters Meet nodes are related to doming of Archean gneisses in the Yavapai time, or in Yavapai time.
Yep, that's consistent with what we're seeing. So if the doming is responsible, if the doming is bringing the heat up and scorching things from below, then that would be consistent with what we see. What drives the doming is another question.
All right. There are no current hands up or other messages in the chat, so I'll give just some time for people to formulate questions if they'd like.
Hey, Daniel, maybe I ask a question. It's
Okay.
a bit broader, but you kind of pointed to it. So for Appalachian and for Scotland, you have this progression of opening or magmatism going younger towards south that you showed nicely.
Oh yeah.
If we look around Superior Craton, the age is not super precise, but some of them relatively precise. So the interesting pattern that it's more or less the same age around all around Superior Craton, at least from pattern that we have now. And so the question, like as you indicated, like what is driving it? You can imagine maybe a mental downwelling and from all sides sort of cratons approach the Superior Craton. But when if you take it even broader, similar magmatism you see all over sort of archean cratons, like in Australia, in Slave, in other places. And it seems to be also associated with initiation of subduction or early stage of orogenesis. So, and some interpret it as a mental plumes, but it's quite controversial. Other don't agree with it, but sort of what tectonic setting would you imagine that would result in this initiation of suprasubduction magmatism more or less always at the same time on all sides of Superior and in other places in the world?
I mean, yeah, so I expected the Appalachian Caledonian system to give very similar dates for the ophiolites when we started this. But it didn't. The range ended up being much more significant than I thought it would be. I mean, if instead everything had been 490 million years old over 6,000 kilometers, then that would suggest that there is a very extensive region of the margin or some inboard region, some sort of outboard region within the Iapetus that was just primed to go. So whatever it is, it needs to be associated with either some sudden event, and I know that the large igneous provinces in the Circum-Superior have been associated with plumes, or else just a system that is critical, it's ready to go. And on that later note, we're initiating some new work trying to understand the context and potential setting and drivers for subduction initiation within the Iapetus Ocean. So within the Wilson cycle, the classic Wilson cycle model. And I think that what is an important factor here is that the Laurentian margin was hyperextended, and that there may have been some oceanic tracts that just weren't comfortable. We're ready to go, and once they start, it's a cascade. And so rinsing these little oceanic tracts that sat between continental fragments, allowing the system to merge back together. And so, yeah, I'm not sure what process could be responsible, but I would think that it would have to be have to be a system that's departed significantly from equilibrium, and is therefore supercritical, ready to for this sort of cascade of events to occur.
So obviously, it would be very interested to get high precision ages.
Yeah.
Because it's still possible that there is some like on the order of million years progression of ages. But another thing I was always interested, if there is a potential that when you have a subduction and you subducted already significant part of the ocean, but collision didn't start yet, but you initiate mafic magmatism from mental, maybe not necessarily mental plume, but sort of mental magmatism as a result of this replacement of sort of creating a continental lead where used to be an ocean, and sort of deriving magmatism this way.
So sort of a back arc style.
Yeah, but sort of you replacing sort of thin oceanic crust with continental crust, and you creating thermal instability and driving mantle magmatism as a result of it. So actually, whatever large igneous provinces could be linked to subduction of significant part of the ocean, but before collision started.
Yeah, there's been recent work that suggests that the mantle potential temperature in the Circum-Superior was relatively homogeneous, which is not consistent with the plume model, and would require that potentially this is driven by some tectonic event. That would also explain why it's such a long, it's such a linear system.
Mm-hmm. Thank you.
Thanks.
All right. I'll leave a few seconds for anybody else to raise their hand or come up with a question in the chat.
And on a different note, we starting to put a schedule for the fall. So if people have suggestions for potential speakers, you can either email us, or I think maybe Alex still have a form to fill on the web, sort of suggesting potential speakers.
Yeah, I don't know if we checked that recently, so maybe we should check that, Andre. Okay, thanks a bunch, Daniel, for a good talk and good discussion at the end.
Well, thank you, Alex, for organizing everything.
Thanks, Daniel. See you.
See you, Mike. Go O's.
Thanks, everyone. See you next week. Take care.